Okay, so let me just conclude with the most general result. Along Zalberger lines was we take x goes to P1k f x smooth projective, and then we assume that for all close point P in P1k there exists a component y in the fiber xp, which is of multiplicity component of multiplicity 1, with k of p sitting in k of p algebraic inside k of y, and this abelian. And then this is 1, 1. And then the second assumption was that for almost all points, put little m in P1 of k, the Hasse principle plus weak approximation hold for for all m close point, for all m in P1 in close point, hold for the fiber xm with fiber smooth fiber, then conjecture E holds. So I write 1 second conjecture E for those who are not in the first lecture. So the conjecture is that CH0 of x hat, which is the projective limit of the A mod n, goes to product for V and omega of the CX0 of xkv dash n goes to hom power of x q mod z is exact. Okay. And this little dash has to do with the Arcadian primes. So we managed to, pushing Zalberger's argument and getting rid of the algebraic case theory, we managed to prove this result with Swindler and with Skor-Bogatov. So any fibration like this hypothesis that the fibration is geometrically split, but also that at any point, all the points really, when you look at this complement of multiplicity 1, we want a complement of multiplicity 1 such that the algebraic closure of K of P in this is abelian, which is a big nuisance. And then also we wanted to ask the principle of the fibers. And then we conclude this is not an unconditional theorem. We have conjecture E for X. And weak approximation for the fibers over any field extension. So if I take any fiber, so this is the case for conics, for instance, which we had for conics. Okay, so this is the case I showed for conics. This extends to this setup. And it's this argument. So remember, I told you that for rational points that initially we had theorems like this, with rational points with also this condition, and modulo Schinsel, we could prove that Baromani is the only abstraction for rational points. And here there's no Schinsel, it's an unconditional theorem, but we still have these restrictions on the fibers here that they are special. We cannot handle the case when there are counterexamples in the fibers. Okay?
Say, if you take a family of cerebral varieties with degenerations,
yeah,
does it
satisfy this? Yeah, example. This is the basic example. Yeah, this is the basic example. The other basic example is family of quadrics over P1. So 3-dimensional is trivial, but 2-dimensional is not trivial, and it falls into this case. Okay. But for instance, the thing we could not handle was case of families of dead Puzzle surfaces of degree 6, which are very simple objects. They satisfy the principle, but this condition we didn't have.
What is this condition?
So you take the ground field of your component. The component is defined over KFP. So you have the function field. Then you look at the algebraic closure of KFP inside here. Actually, algebraic closed inside K of y, and you want this to be abelian. And somehow it's the same problem we had. We were constantly using bra of k, direction bra of kv, it goes to direction of q mod z. So what Harpas and Wittenberg have done is that they managed to get rid of this by replacing this sequence by the Poitou-Tate sequence. We'll see that. Okay? Right? Yeah?
One more question.
Yeah.
Yes. Say, can we take family, there are quadrates, there are family of conics, there are family of Severi-Brauer. One could ask, say, family of some, I don't know, take a
homogeneous spaces.
Project with homogeneous spaces.
Yeah, project. Same problem. We don't know about it. So they satisfy this property. This satisfies this property. Okay, projective, but not this one.
Just say if you take an exceptional algebraic group like E6, exceptional groups up to some extent much easier in fact than the standard series A, B, C, D.
Well, but the question is, do you know? The question is very simple. You have a discrete variation ring. Over the field of fraction, you have a projective homogeneous space of such a group. Do you know that you can produce a model of the special fibers such that this condition is fulfilled? I don't know. And possibly in some cases you can do it.
Question for some people in the audience.
Sure, it's a question. Huh?
I mean, for the value of
yeah.
school, this really is a good question.
I mean, even,
discrete relation, and even over complete, I think, discrete relation.
Sure, it's a question about, it's just complete. It's just a question about complete discrete relation. But in general, it's not true, because in general, you can always do stupid things like you can take L over K, which is quite bad, and you take a restriction of scalars of your space, X over L.
No, sure.
So you get the...
But you see, I take specifically not...
okay, you're not... Oh yeah, you want the group to be simple. Yeah, absolutely simple. Okay, absolutely simple. Yeah, absolutely simple. It's possible that you get something. Yeah. Okay, so anyways, so we were at this point. So we were stuck for some more. I mean, so we had problems with this. But before in the end of the lecture, I will explain what Harpas and Wittenberg have done. But I will do something easier at first. So I'll describe some work of Yongxi Liang, who is somehow a grandson, because he's a student of Harari. So the topic is if we have the information on x of k top equals x of a k bro, do we get conjecture E? For 0 cycles. And not only over k, but over any k, any number field. Okay. Multiplicity 1. Multiplicity 1.
Ah, 1.
1. I mean, conic bundles is exactly the situation, because you get this thing here. So what I mean by having the information on x of, so for instance, for tori, smooth compactifications of tori. Of homogeneous spaces of tori. So for tori, this property we know. So work of Ossensky gives us this here.
Okay, may I take back to this conditional abelian extension? So can it be resolved by choosing a specific model of a discrete variation ring? So given a I don't know, principal projective homogeneous space over the function field, over the.
I mean, if you can do it locally, you can patch. It's not a question. So you can patch. I mean, from this, over the Dedekind ring, you can. I mean, there's something which is Dedekind, you can always patch as you want. So it's a purely local question. Yeah. Okay. Maybe sometimes people. I mean, I think you can. Okay. I'm pretty sure you can patch. Okay. Sometimes people pronounce the word stack at that point, but okay. So for there are cases like tori where we know everything is nice. We have the sequence, even the analog of the sequence a0 of x direct sum product of the a0 of x kv bar. For the group of rational points of tori, we have such a thing. And also for the, I mean, this property is satisfied for, anyway, is satisfied for these objects. But what about zero cycles? So it looked a priori something quite difficult. For instance, for the torus of dimension 3, I had no idea how to do it.
And this property with models?
No, this is something. No, I mean, this is something else. This will be this was just I wanted to finish what I said before. This will be connected with what we will have at the end of the lecture. But I wanted to write down a Gerald theorem. That's all. Okay, so here is a baby case of what baby case of a result of Young. So the statement is if we have a class of varieties, so let's say well, suppose we have a class of varieties over a field K, number field K, such that the Hesse principle holds for varieties of that class over any finite extension in that class over any capital K over K finite. Okay, and it's only there that it makes sense. And then the conclusion is then the Hesse principle holds for 0 cycles of degree 1. I take a variety in that class, I'm given the information that it has 0 cycles of degree 1 over its completion. Is there a 0 cycle of degree 1? Mm-hmm. Yeah. So this is easy, but there's a trick to do that, which is very nice. Okay, so
this is the result?
Yeah, this is a theorem. This is a theorem. Mm-hmm. But it's an easy, as you will see, it's an easy theorem. It's just to prepare for the next one. Mm-hmm. But it's when one sees it very nicely. So, okay, so by Lang-Weid-Nisniewicz, so we start with our x, so we start with an x, so we have an x which is given to us, and we have to assume that we have ZVs of degree 1 over each KV. They're given. Given. So if we took the Lang-Weid-Nisniewicz estimates, we know that there exists a finite set S in omega, finite, so that if V is not in S, x of kV is not empty anyway, because the variety is geometric integral. So x over k is smooth, projective.
How does Nisniewicz relate to this result?
Well, all I can say is that this Nisniewicz was around 1953. So I don't know what happened between the two Nisniewicz.
53.
Yeah. So it's not the it's not the other one. It's not the other one.
Okay.
No, it's not.
Okay.
No, but it's Langevin, it's a paper of Langevin, and there's a paper of Nisiewicz approximately at the same time. It's the fact that if you have a variety which is geometry integral, for almost all completions, it doesn't have good reduction. Well, actually, if it's smooth projective, for almost all V, it has good reduction. And then you have the Langevin estimates that tell you that if the cardinality of the finite field is big enough, then there's a point over the finite field, and then you lift it to a point over KV. Okay? Yeah? That's, sure. That we know. Huh? Yeah. Okay, so for V in S, okay, now next step. So next step, so I do it in order. So I fix a closed, so my X is given to me. I don't know whether it has a zero cycle of degree 1. So but there is certainly a zero cycle, so I fix a closed point, M, the outside closed point in X, and I suppose the degree of K of M would be some integer. Okay, so there is certainly a closed point. Okay. Okay. Now for V in S, we take our ZV, which is of degree 1, which is given to us, and we write it as a difference of two effective cycles. So positive coefficients. Yeah. Okay. And then you define ZV1 to be ZV plus n minus 1, this n here, times ZV minus. So this is effective. Okay, I'll take this ZV1 here. Okay.
What does it mean?
ZV, sorry?
Degree 1. Okay.
So this one was of degree 1. This is of degree 1.
Okay, sure.
But now we look at an effective cycle, which is now, well, of degree, I mean, whatever it is. I mean, we've added this n ZV minus 1, okay? But the degree of ZV1 is congruent to 1 mod n. Okay, so now, okay, we have finally many ZVs here. So we're going to add a suitable multiple of n. So for each V in S, find NV, which depends on S. And then you take ZV1 plus NVM. They're all the same degree, all of the same degree. Degree congruent to 1 mod n. Okay, we can add, of course, the ZV1 are not all the same degree, but they're congruent to 1 mod n. So we can add suitable multiples of this m of degree n to each of them in order to arrange that they have the same degree. For V in S. Huh? Okay, so I don't know, do I call it this Z2V? Okay, so they have the same degree. And now here's the trick. So what you do is that you replace X by X cross P1. So you will love this. So you look at X cross P1, and you have the vibration to P1. Okay, so on X cross 0, we have this ZV2 here. Well, ZV2 is some zero cycle of degree whatever, and X cross 0. Well, you can move it. You cannot move it in X cross 0, but you can move it in X cross P1. So you move it, ZV2, and you transform it into a zero cycle ZV3, of this, which is rational equivalent.
As a positive cycle.
As a zero cycle.
As a positive zero cycle.
As a positive zero cycle, you move it in such a way that the ZV3 is nice with respect to the projection to P1. So that ZV3, when you project it by the projection to P1, P, you get something which is, they're all of the same degree. Here the degree is 1, here the degree is 1, here the degree is 1.
Okay. So you can do that?
Yeah, you can do that, yeah. You can, yeah, I'm sure you can do that, yeah. I mean, okay, think of a, yeah, think of a, okay, let me yeah, picture of an example. So I have, okay, I have you know, all I want, in fact, you know, I just want this. In fact, this I want very little about this point. I say rational equivalent. Yeah, okay. So I have a point here, and I have two conjugate points. So I'm over the rails, and I have these two conjugate points, and I want to move this thing to something which gives me that two conjugate points. I'm over the rails, and I want to move it in such a way that, in fact, it projects nicely. So, how should I put it?
The two conjugate points.
I mean, the point is that in this case, C of R and C of C is very small. So you can move it. So I will see in the proof whether I really need rational equivalent. I mean, if I don't need rational equivalent, then it's even simpler, because it's clear that I can do that. So why did I write the rational equivalent? I'm not sure I need rational equivalent. I think I don't need it. It's completely psychological. Yeah, I'm sorry. No, I think I don't need rational equivalent. I can find, all I say is that I can find a ZV3 exactly of the same degree so that the projection is nice.
It's not rational equivalent.
No, it's not rational equivalent. So well, I would have to think. I wrote right, but I think I don't need it. We'll see. I think this is enough. So we have the ZV3 projecting nicely here. And that's the argument here. That the reals are very small in the complex. And similarly, if you have a periodic field, the part which is, you know, if there's this thing of degree D or next, well, you can, well, yeah. Okay, so maybe assertion, and then you assertion. There exists Z3V, same degree, that's important, such that the ZV3 projects 1 to 1 to P1. Okay? Now, rational equivalent, I think I went too far with rational equivalent. I think I don't want. No, this is too much. I mean, okay. So I mean to convince you. So what do I want to? The simplest example is. Okay. Well, let's accept this point. Let's accept this point. Okay. Okay. And so now, so what do we have? So we look at the projection P star of Z3V. So this is a zero cycle in P1 over KV. And it's given by a polynomial GV, again, GV of T. I'm describing the zero cycle here. Okay. Take this GV of T. Okay, and then all we do is that we do take say monic. This contains A1 KV with the parameter T. Take G of T, monic, close to each GV of T for V in S. Okay, then what happens is what? Well, if you look at, and so you can take it irreducible if you want, irreducible, same trick as before. Then you look at the close point corresponding to this, and then you look at the fiber over this close point. That defines a close point of degree congruent to 1 mod n. Okay, congruent to 1 mod n. And then above this point, we have a field L. And now the fiber XL, I claim that XL of LW is not empty for all W. Well, for the W's which are above the places in S, is because the G of T was very close to the GV of T. And for the other one, it's for free. Here. Okay. So this is free for W above a place V which is not in S. And this is OK for W in S above a place V in S because G is very close to GV.
So in the first case, free for W over V which is not in S. This is this condition.
Yeah, because for the places which are not in S, you always have points locally. So this is true over any field extension. Okay, and so now you've produced a variety of that type over some field L, which has points in low completion. We assume that's the principle, so it has a rational point. And so now we have a rational point over this field L, which is of degree congruent to 1 mod L. And then we have this close point of degree n, so there's a zero cycle of degree 1. Okay, so what was used here is simply Krasner's lemma, saying that when your two points are close, you get the same situation. Okay, and then well, of course, Nisniewicz, Langway-Nisniewicz, and this trick of moving something which is taking x cross P1 and then moving to something so that it becomes isomorphic here.
So my question is, not about the proof, in fact, but about the relation of the statement of the theorem to the one of Zalberger you explained. So
no. You see, I mean, no. Okay, the scheme is what? The scheme is Zalberger's result is an unconditional result about zero cycles of degree 1, if you want, when you only had a conditional result about rational points via Schinsel. Okay? So you have the conjecture about rational points via Schinsel, and then you have a conjecture about zero cycles of degree 1. So the one by Schinsel, what's the conjectural? So we can, I mean, of course we could try to use it, but if we have an actual proof for zero cycles of degree 1, it's better. Whereas here, you start with a situation where we know the situation about rational points, and then we deduce it for zero cycles of degree 1. So it's a different direction. Okay.
And what's the problem with rational equivalence?
No, I think I think it's not correct that I can move it to something.
So if you have a point in X with any coordinate on P1, so with zero coordinate on P1, you can just produce a curve for P1, which
goes through the point.
Just goes through this point. And
so I mean, you mean you reduce it to a problem about, so you want to reduce this to the case of a curve. So okay, I agree. You can.
No. So we have just X cross P1, yes.
Yeah, for X cross P1, yeah.
And here we have P1s that are parallel to P1.
No, but we don't have the P1s because we don't know whether there are rational points on X.
Okay.
So if you take a close point, you take something which is a close point, it won't be parallel. It will be there will be a degree.
It will lie in P1.
Suppose X is a curve.
If X is a curve.
Yeah.
C cross P1. Well, it's the same problem. I don't see the.
Sure.
Yeah, I don't see.
Don't see.
No, I don't see. No. I think it's probably.
Reals. Say, I would like to understand over reals.
So over the reals, the question with the complex and the reals. Okay. So complex with the reals. So okay, over the reals, what do we have? Okay.
And with the, I mean,
so
X is curve.
so X. So okay, C and C cross P1. Okay. And so we have a complex point. Which a priori, because it's over 0, so you have two conjugate complex points. And the claim is that we can find, in this situation, two on X cross P1, we can find a complex point which doesn't map to a real point. That's all I'm saying. In this, in this very special case, it's even trivial. So it's that so X of C doesn't map to P1 of R.
And in fact, these two points
inside the P1 of C.
These 2 points have nothing to do with the original.
No. In fact, you see, it's just a degree argument. So that's all we want. So it's very weak. I mean, this is an easy theorem, and it's not. The next one would be better, but it's just to show this trick of X cross P1. Yeah, I mean, so in this case, it's exactly this. You see that. It's not possible because X is smooth. x of c is not reduced to x of r, and x of r sitting in x of c is very small. Yeah, I mean, this one, at least I hope you believe this one. That is.
Move this point. Just.
No, it's not moving. It's finding another point close. So no, in fact, it's what it is. It's this thing. Now, what you're doing is that. Okay, I'm sorry. I should have said it like this. So we have x goes to y, and we have a local field kv. Okay, and then we have a closed point inside here. So it lives in some finite field extension. And so now we have x of capital kv here, and then you map it to y of capital kv. And you want initially the point you had was mapped into a point in y of kv. This was the problem. And the thing is that when you take the implicit function theorem around that point, it's impossible that all the points given by the implicit function all map into the union of the y of kv for the so you have finitely subfield extensions. But this is very small inside y of kv.
Speaking by dimensionalism of locally compact field.
Yeah. That will do. Yeah. Dimension. If you use the degree, finite degree map, you use a finite degree map, and then you can do the argument plus dimension reason. Yeah. Okay. Yeah. Thank you. Okay. So the next result by Yang-Xi Liang is more striking. It's not much more difficult, and maybe because in fact, wait, it's 2:30. I should be reasonable. I just state the theorem, and I might jump to the Harper's. Okay, so theorem by Yang-Xi Liang. So this is really a theorem. So you take K a number field as usual, X smooth and projective as usual. Chebyshev connected. Now, assume, as usual. Now, assume that H1 XOX is 0. H1 XOX is 0. And that, H2 XOX is 0. And that the Picard group has no torsion. Okay, now, and then you also assume that for any number field K containing K, so in the text everywhere I write for every finite number field extension of little k. So I discovered that the finite could be dropped. Okay. Little k. We assume that that x of k top is equal to x of ak br. So we assume the conjecture for the rational points, the conjecture that the Brownian obstruction is the unobstruction and this density property over any field for the rational points. And then the conclusion is that the conjecture E holds. Actually, let's say conjecture E1, the way to put it, holds. So that is, if there exists a family ZV, V in omega degree ZV equals 1, then orthogonal to prob of x, then there exists a zero cycle Z and Z0 of x of degree 1, global 1. Okay. In fact, it proves more. It proves more, but not so. I just state this one. Let me mention the more general result it proves. Well, not more general, a bit more assumptions. If, moreover, x over k is geometrically irrationally connected, then conjecture E, the whole conjecture, holds for x. Okay, so if the variety, so if you take a variety which is geometrically rationally connected, in fact, these conditions are fulfilled up there. These three conditions. But so if you make this, this assumption, the whole conjecture E about 0 cycles, the one I wrote again, is satisfied for X. Assuming this, of course. Okay, we assume that we know for everything for rational points at all finite levels, then one deduces it for these varieties. So applications. So this was really quite the result. Application. Conjecture E holds for any X containing U, where U is a homogeneous space of a connected linear algebraic group with connected geometric stabilizers or connected isotropic groups. And so you take a U, there's a group G acting on X transitively, and then for X in U of K bar.
With geometrically connected stabilizers or with connected stabilizers?
With connected stabilizers, yeah. I mean, what I call isotropic group is the same stabilizers, if you prefer. I mean, the definition is, if I take G acting transitively on U, if I take any point in U of K bar, the question whether Gx is connected doesn't depend on the point I take. Geometrically connected, wait. Geometrically connected, yeah. Yeah, geometrically connected. Stabilizers, okay? So because the point is that in this setup, this theorem is known, it's work of Sansuke and Borovoy. So Sansuke and Borovoy handle the case of rational points. And so from this theorem of Young, you get the result for 0 cycles.
So may I ask you
yeah.
question? So particularly, can I take substitute X to be projective homogeneous space?
Yes, but in the case of a projective, well, okay, so if I take a projective homogeneous space
with the same conditions that stabilizers are geometrically connected.
No, but they are connected. They're always connected. They're always connected.
Yeah, okay.
But in that case, what happens is that.
Formally, it does satisfy your condition.
Yeah, okay. It's a non-trivial. Well, there's one part of the result which is probably quite trivial, is the part about. No. Nothing is trivial,
No.
because even A0, as you know very well, is not automatically 0. It's not clear.
Even
The Char group of 0 cycles of degree 0 is not. We don't know whether it's always 0.
Sure.
So even E0 is not clear. Yeah. You're right. Even that case is interesting.
Formally, it does satisfy the.
It is okay. So it applies. Yeah.
It applies.
Yeah. I mean, so it's well known that if you take a projective homogeneous variety over a number field, if it has a rational point, it is birational to projective space.
Okay, sure.
So it satisfies weak approximation. On the other hand, it is also known that once you have the principle for the semi-simple simply connected group, well, harder proved that if you have, once you have the principle for simply connected groups, semi-simple simply connected, then you have the principle for projective homogeneous varieties over a number field. So the Severy-Bauer case is just one case. I mean, it's known in all cases.
Okay.
So these are special cases of the theorem of Sansuke and Borovoy, of course, but they were known before.
But something I didn't get.
Yeah.
I'm about the conclusion rather than about.
But the conclusion is conjecture E holds.
Yeah. And theorem of Zalberger was about theorem E0 and E1.
So Zalberger is about I mean, this is a situation where basically you have a nice open set, which is a homogeneous space, which is really nice. Yeah? It's smooth all over the place. Yeah. Of course, you might have something at infinity, but Zalberger is about something where you have vibration over P1.
Okay. Or vibration over
P1. So in fact, you have bad fibers and. Yeah. It's another setup, but this case was very interesting because the case of tori, we thought even the smooth condition of tori, we didn't know how to do it. So this is what this result of Liang has achieved. And I mean, I think I should not go through it because basically, this is the reason why I did the baby case, is that it's this X cross P1 does the whole trick. You also use that bar group of X is isomorphic to bar of X cross P1 in the argument. And you, well, it's in the notes and it's really basically the same idea. So, but the result is spectacular. Just this trick of it, basically it's just this trick of taking X cross P1. So that was really a nice result. Okay, so and so one thing I should say is there's a difference between the assumptions here and the assumption here. Yeah, okay, so okay, this is a situation that the bar group might be non-trivial. Okay, so what he has to do, just a couple of words about the difference between the proofs, is that you start exactly in the same, so a couple of words, proof, but it's very short, it's just a sketch. You start in the same way with your X cross P1. And you find these nice, for the V in S, you find these nice ZVs. Okay? So, and then you approximate GV of T by a G of T. And then you find a close point, M, so that XM, find M, with XM, which has points, LW, not MT, all completions, all W, in omega L. Okay? Over the field M, where M is the real field of M is L. Okay, fine. Now the problem is that you want an adelic point which is orthogonal to the bar group. So you find this family PW in XM of AK. And you want, what you would want is not only PM in XM of AK, but you want PW in XM of AK bar group of XM. You see, you want the information is that if this set is not empty, then there's a rational point in the fiber. But all you have produced by this process is simply a point, an adelic point in XM. So the question is to produce the point M in a nice way. So you want the map from bar group of X cross P1, which is bar of X, to bar group of XM, the evaluation map, modulo bar group of the constant, so modulo bar of K. You want this map to be onto. See, because you started with a point which is orthogonal to this, and you want this map to be onto. So it's like Hilbert, so it's a kind of Hilbert-Reducible theorem, except that you want to apply it to close points. And one can do that. There's also, usually when stated for rational points, but there's also a Hilbert-Reducible theorem with respect to close points. So this is, in fact, one component of what Liang does is to apply suitable Hilbert-Reducible theorem with close points. So I don't want to say more about it, but that's the basic point. Okay. So remember, in Array's argument, we had this family over P1, and there was the bar group of the generic fiber, and we wanted to subject onto the bar group of a certain special fiber of a rational point. Well, the same principle here. You want to sujection like this. And then you get a point which is actually orthogonal to the bar group, and then you apply the hypothesis you have here. And then you produce a point in the fiber of XM. That's the principle of the proof. And here, the difference between the two parts here is that we have a stronger assumption. And the stronger assumption is in order to take care of the char groups, the A0 of XKV, they are 0 for V not in S. And that's work of Kolar and Szabo. So Kolar and Szabo have studied the char group of 0 cycles on rationally connected varieties of a local field. And they have shown that this group, in fact, is very small for almost all V. So if a rationally connected variety of a p-adic field has good reduction, which is the case for almost all V, then the group of 0 cycles of degree 0 is trivial.
But good reduction means smooth?
Yeah, smooth, regular. I mean, you have a smooth fiber. Of course, the geric fiber is like this, so for almost all V, you'll have an X over a spec of the finite field. And I think it's even known that just under the assumption that it's smooth over a spec OV, the special fiber is also rationally connected in a strong sense. Then they proved this. Anyway, they proved this. Okay? And so this goes into the proof of E.
This group is very small.
This group, well, no, we don't know. That's a, okay, this is another story. Okay.
So
the statement they proved that the smooth fiber exists. So Colliot-Thélène proved that if X over K is given, rationally connected, then there exists S in omega, finite, with X of KV, 0 of KV, 0 for V naught in S.
For instance, S is empty.
No, but in general, it's, no.
For any...
No, X is given. There exists some S finite, from set of bad places, where A0 of X KV is complicated. For V naught in S, it is 0. Okay? For almost all V, the group is 0. So that goes into the proof of the whole conjecture E here. And so that's why the assumption here is stronger than there.
So this X is rationally
connected. Geometrically rationally connected. Yeah. So it's a very beautiful paper of Colliot and Szabo where you use oh, it's already maybe 6-7 years. It's a
90s or
no, it's more recent. No, I think, yeah, because this whole business of rationally connected variety of a complex field started just over the complex, started in 1990 approximately, and then for 10 years it was only in the complex, and I think 2002 Colliot had this great idea I mean, there were some special cases which I knew, but no idea about the general case. And Colliot had this great idea of using these deformation techniques over the complex over local fields. And the whole point is that if you look at the proofs of these deformation techniques over the complex, is that they use the fact that if you have a situation like this, which is étal at that point, above this point there is another point. But it's also true over the p-adics, over the rails. You know, if it's étal Nisniewicz here, then there are lots of points. So you can deform. So normally they have a game where they deform. They have some trees of P1s. They deform it to something nice. And to deform, you have to go along a curve like this and find some other point. But over the rails, the p-adics, it also works. So Colliot started this business, and so basically, I think between 2002 2007, there were quite a few papers on this topic. Okay, so much for Jan. And so now we try in the remaining time, whichever remaining time there is, to explain. So first of all, I will state the big theorem by Harpaz and Wittenberg, and then I will try to...
Sorry, I wasn't present at the beginning.
Yeah.
Do you know how is conjecture E known in some geometric situations, the arithmetic ones?
Well, the conjecture E is over global fields. So you can ask it over a number field, or you can ask it over FQ of a curve.
So not for C over
Not for C over C, there's no... I mean, for rational points, there's an analog. But for this conjecture about E0, in fact, I've never thought about it. No, in fact, I don't know.
Okay, thank you.
No, I do not know. I mean, the thing is that the conjecture involves reciprocity. The complex one writes down is built on the fact that we have the basic exact sequence bar of k, direct sum bar of kv, q mod z. So if you wanted to do something over something like C of a curve, you would want to use some reciprocity argument. So you can do some reciprocity argument. You can take H1. So it's n mod 2 to make them simple. Then you go to the direct sum of all the various completions.
Q mod z.
No, I can take, Q mod z, why not? Yeah, Q mod z, let's see. I mean, I don't like Q mod z because I should write the twist. That's why I write that. Okay, but okay. Well, let me ignore the twist then, if you want. So let's say put a 1 here. And then we have the direct sum for all the points P in C of the H0 of C q mod z, and then we have the sum to q mod z.
Sure.
Okay, so there's a reciprocity here.
The property, yes.
And so you can do this thing, but then what the object instead of the bar group, the only thing you can play in that case will be the pi one, h1. So you can do this with h1 of x with coefficients in q mod z of 1, which is the abelian covers of your x. And in fact, we have written some example. So in fact, in the paper with Philippe Gilles, we have an example of no, but it's about, well, okay, the thing we thought about was the local rule principle. We didn't think about the CH0 business. So we have an example of an n-recursive surface over such a thing, which has points in all the completions, but doesn't have a point in the global field by reciprocity. And I'm pretty sure that it will get the same thing for 0 cycles of degree 1. But the A0 part, we never thought about the A0 part. I mean, the part Char group of degree 0, modular rational equivalence, I don't know. I haven't thought about this. No, it's a nice question. Okay, so the big theorem by Harpaz and Wittenberg, which somehow is the end of a whole year, 2004, is we take x smooth projective geometrically connected and rational okay, and we have a morphism from x to p1 dominant, and x theta is supposed to be geometrically rationally connected. If for all m in u of k, u is some open set in p1k fixed.
What is the condition of f? Sorry.
F is dominant.
Ah, dominant.
I mean, you know,
Okay.
you know,
Okay.
in France, people will say, "Oh, but if the image is a point." Okay, so if for all m in u of k, xm of a k, I'm sorry, how should I put the hypothesis? If all m in u of k, conjecture E holds for xm, I'm sorry, it's m in u, a close point, holds for xm over the field k of m, then conjecture E holds for x. Some u, there's some u. You can make it as small as you want. I mean, so, and there exists u, if there exists u, not empty. So it's for m in u in p1, sorry. Close point, the conjecture E holds for xm, then the conjecture E holds for the total space. Okay. And so the corollary to illustrate on a concrete example, the corollary is that if you take x goes to p1k, if x theta is smooth compactification of k of p1 homogeneous space of k of p1 connected linear algebraic group with geometric connected stabilizers, then conjecture E holds for x. It's a concrete general result.
So again, my question is, so particularly we can take
You can take x theta to be a delta to the surface of degree 6, which we didn't know how to do.
Yeah, yeah.
Okay.
I'm thinking
Yeah.
in a different direction, maybe more simple.
Yeah.
So when you take a projective homogeneous
Space.
X eta is to be, suppose that x eta is a projective
Yes.
homogeneous space
Yeah.
of the gene. Yeah, projective homogeneous.
Yeah, that's an example.
That's an example.
And that's an example which we didn't know how to do. So we didn't know how to do that one.
But
Except for cases.
This is not a claim about. This is not a statement about conjecture E naught and the conjecture E zero and conjecture.
It's everything. E0, E0, E1. E covers E0 and E1. Yeah, E. No, E.
But I asked you before the break about this example. And you told that this example for if in the fiber we have a principle. We have
principle. Yeah.
If in the fiber we have in the generic fiber we have projective homogeneous space.
Yes.
Projective homogeneous space.
Yeah.
You told that Salter's theorem is not known.
It was not known.
Yeah, it was not known.
But now it's known. So I mean, it was not.
Before the break, it was not known.
No, but before this theorem, it was not known. That's what I'm saying. We didn't know how to get it. That's sorry, maybe I didn't. We didn't know how to get it, but I mean, they managed to prove it. They managed to prove it. Okay, and it's very, I mean, a priori you could even initially, even simple case when the group was constant, you could ask about a group which is constant over K, but even that case was not clear. Okay.
So particularly, not only for the family of quadrics.
No, it's absolutely, it's very general.
Any generalized flag varieties.
Absolutely, yeah.
It does hold.
It absolutely, yes. The answer is yes. Yeah. The answer is yes. Yeah. So the abelianity condition has disappeared. Of course, in the case you mentioned, if you take projective, then it has a principle holds in the fiber, so you don't have to worry about this. But the abelianity condition has disappeared.
Yeah, it disappeared.
Exactly. That's the point. Okay. So I mean, I should say, so I mean, the abelianity condition, of course, in the cases, in a case like this, when the Jerry fiber is geometrically rationally connected, we know that it is geometrically split by Graeber-Harris star. So at any close point, there is a component of multiplicity 1.
Okay.
But this abelianity condition well, that we don't know. Okay. So the abelianity condition has disappeared.
This is called the achievement of this proof.
Of this proof, yeah. Well, the abelianity condition disappeared, and also the Hasse principle plus weak approximation in the fibers have also disappeared. See, in the string of papers, Zalberger, myself, Swindendara, Skobogatov, we always had these two conditions: abelianity plus this condition here, and so they've disappeared completely. Yeah, so it's completely general as a result. That's so why it's very. I mean, it's really quite something. Okay, so now. So I hope, so I have one page. I want to show you one idea on the proof, and then this will be the end. So either I stop here or I go through this one page. So
maybe you could start. I mean.
Next time, no.
Yes.
No, because next time I do something different. I like the unity of unity. So it's like classical tragedy: unity of action, unity of time. Next time I'll talk about something different. Okay, so the special case. So I want to discuss the special case. So we take special case where we take x to p1k of fibration. And then we assume the non-split fibers are above k points, because otherwise the notation becomes very complicated. So t equals e1 en. Okay, and that's so over each of these k. Sorry. these map points, EI. We choose a component, what is it? How do I call it? EI, yeah, of multiplicity 1. And then we have the algebraic closure Ki of K inside K of EI, which is not abelian, which is whatever it is. Okay, now we let U, so okay, so assume, assume what? Assume that there exists an adel PV in X of AK, which is orthogonal to, in fact, to bar X divided by bar of K, but in fact it's enough to assume that it's orthogonal to bar vertical of X divided by bar of K. These are the elements of bar of X, which to the generic you go to the generic fiber, they come from bar of K of T. So it's a subgroup, that's enough, okay, for what I want to prove. Okay, then for all n integer bigger than the degree, the n, possibly it's n equals n is okay, but let's ignore it. There exists a close point, M, close point of P1k of degree n, such that the fiber xm is smooth and has points in local completion. Okay. So if you remember what I discussed with rational points, I was when I discussed rational points, and I was discussing the work of Hoppers and Wittenberg, there was a similar first case when we had a family like this. And we said if certain conjecture HW star star, which they have made, is true, then we'll be able to find first a rational point on the base such that the fiber has points in all the completions. And then I went on by using this error bar on top of this XM. But this was the first step to see what happened. Okay? So here we're doing this, and there's no abelianity condition. So this is what I want to illustrate how you get this. Yeah? Okay, so we start, so I assume something simple. Instead of starting with zero cycles, I start with rational points. It's simpler to write down the arguments. So we have this x over P1k, and let's say u is the complement, is P1k minus infinity and the EIs. Okay, and so you have xu over u, which is smooth. And okay, so and then, so here, the starting point. Starting point. Formal lemma for torsors. Okay, so this R is formal lemma for bar group, but we have a formal lemma for torsors under a torus. And so we look at on xu, so we have u, we have xu over u, and we have the coordinate t, and we look at the torsor given by t minus ei equals norm ki over k of variable xi. So this is a torsor under what? Under the product for all the i's of the R1 ki over k gm. This is a torus which is involved in this story. Not the product of the norm 1 elements. Okay, this is a torsor. If I take the I range from 1 to n, I produce over u and over xu a torsor under this torus. So if you apply the formal lemma, yeah, before I forget, before you leave because you're tired, there is this conference between the 16th and the 20th of June. So there will be, I mean, people will talk about much of the topics I've been talking about. And so I would make a recommendation is that you register on the website because you'll get free lunch. Okay. But it's also good because we know who is coming, and so okay. So. Okay. Okay. So we use the formal lemma, and the formal lemma.
The conference will be at П.Л.Чебышева.
At 16-20 June. П.Л.Чебышева, Fontanka. And 16 is a Tuesday, okay? So the formal lemma produces some BIs in K star such that what? Such that if we look at the variety, so that there exist points MV in with coordinate TV downstairs in XU of KV for each V and S. So MV. So it is for all V and S, for all V and omega. I'm sorry. MV goes to TV. TV is in KV. This is the projection. Such that TV minus EI equals BI norm Ki over K of psi IV.
What does it mean minus?
Minus TV minus EI. TV is an element in KV.
Ah, okay.
So it's a function T minus EI which we apply to the point MV, which is called a TV. So it's and this is different from 0, okay? So when produced above XU, we produce some. So initially we started with 1 here, but we produce this global thing, which is this thing that comes from Poitou-Tate ultimately, okay? And so we produce this torsor here above XU and this torsor here, and now we have this adelic point here, which actually comes from an adelic point about this global object, T, which depends on B1 or Bn. Okay, so we have this property. Okay, now we start, in fact, basically the trick which we saw in Zalberger. So with rational points, we're stuck here. We have to use this big conjecture of HW star of Harpas and Wittenberg if we want to get rational points. So we extend, and so we push this. So with this point which we had, this TV, and maybe I call it alpha V now. Alpha V here. I'm going to produce more points. Alpha V1, implicit function theorem, alpha Vn. So where is the one? The n. The one is okay. N. This capital N, and I produce points on top. Okay, they're very close. I mean, I have a point here, so I can move analytically. I get something, and I get some points like this, and I take n points like this. Okay. Then I define GV of t to be product j from 1 to n, capital N, of the t minus alpha Vj. Okay. Okay. Now I do my Euclidean division.
Did you get rid of non-abilineality already?
Yeah, at this point. We use the formal lemma for torsors, uses torsors and a torus, which need not be split by abelian extension. That's the point.
Okay.
Okay.
And Dirichlet theorem, blah, blah, blah.
No, in fact, it's hidden. I mean, it's hidden basically. No, all that's used here is basically H1kt, direct sum H1kvt goes to H1k t hat dual. Exact, yeah, exact. Yeah. And Dirichlet theorem, no, we don't pronounce the word Dirichlet theorem, but it's very complicated because in class field theory, Dirichlet, the things that come from L functions are behind the scenes. So I'm not strong enough to tell you whether one can prove this without using L functions, and so.
Dirichlet arguments are not. They were used.
They were used in the previous argument. No, they don't appear here. They don't appear. They don't appear here. In fact, there's one point. We'll come to that point. We'll come to that point. There is one place when we use Dirichlet, but in a very weak form. Okay. Not as strong as this precise one we had. Okay. Okay, so we define GVFT, this is the definition. And then we do our Euclidean division. So GVFT. Now, the previous time, the example I gave you, the polynomial P was irreducible. Now it's not irreducible because P of T is the product of the T minus EI. Okay. And in fact, here, I've been using the fact that the thing was orthogonal to the Brauer group. Previous case, there was no Brauer group because the P was irreducible. This case, there is a Brauer group and we have used it. We have used it in the formal lemma. So when using the formal lemma for torsos, we were using the fact that we had some adelic point orthogonal to the Brauer group. Okay. So we have P of T here. So the division we make is the following. We write GV of T as P of T times QV of T plus sum I equals from 1 to D of product from J different from I of the T minus EJ divided by product J different from I of the EI minus EJ times GV times a constant, which in fact is just GV of EI. What I'm doing is I'm doing the decomposition like this. I'm doing something which you all do, is you know how to, when you have this P of T, it's isomorphic to the product I running from 1 to n of the k's. I'm just making this explicit. Okay,
okay, so interpolation polynomial.
Yeah, it's a classical thing, which we know, classical exercise. Okay, okay. So I do that because it's trivial. I mean, you know, there is because P of T is this product of T minus EI. I just identify the things which are here and reconstruct the polynomial. Okay. Okay. So now, so we have to define a set S, bad places. So bad places. So as usual, you take whatever you can imagine. Okay. So in particular, you're going to take, you want the EI, EJ to be in OS. You want the EI minus EJ to be in OS star, etc. Okay, so you take the finite set of bad places. Okay, and now here there's something which I haven't written, but which I have to write, is the thing that's substitute for H star. So I have a problem with room. I'm sorry?
In OV for V is not an S, or?
I want it to be, OS is the integers away from S. So OS, integers away from S, okay? I want good reduction for my whole situation over OS, okay, okay, now there's one lemma to go back to, is a basic lemma proven by these people, which I think I wrote here. Okay, so this is a basic lemma about number fields, which replaces H star star in this context. So what is this extension? Is you have a finite extension of number field, finite extension. So this is Harpas-Wittenberg. Finite extension. It's very, in fact, it's an easy lemma. Okay, we have S is a finite set of places, and then you have elements psi v in little k, yeah, in omega k. Okay. And then you have psi v's, which are in kv star intersection norm kv star. So these are norms, in fact, from there are norms in kv from this field. Okay. Okay. Then there exists a psi in k star such that psi minus psi v is smaller than epsilon for V in S. Xi is in OS union T star, that is, it is a unit, where T is the set of places of K, V not in S, and I'm sorry. Okay, and there exists a place W of capital K of degree 1 over K. Okay, so you are a unit away from S, but also we might have some bad places. But in fact, the bad places all have the property that they are split, if you want, in the extension capital K over K. And moreover, in fact, they do it better. You can fix a V0 not in S, a V0, say, split in capital K. You can fix it. And then the Xi, you can take Xi, and in fact it's important. Take Xi to be in OS union V0. So it's integral. It's integral away from S union V0. And where it is not a unit away from S union V0, then in fact the V splits in the extension L over K. So it's a bit long, but the proof only uses, so the proof uses strong approximation. I won't give it. It uses strong approximation for a fine space A and K minus something of codimension 2. Which I mentioned in one of the other lectures. There's not a fine space satisfies strong approximation. If you take away something of codimension 2, we can ensure that it still satisfies strong approximation. And that's an interesting question, whether it's a general property that if you take a variety which satisfies strong approximation, take away something of codimension 2, does it satisfy strong approximation? We don't know. But for this one, we can do it. It uses this plus a mild case of Dirichlet. And so when I say mild case, it's because, as Wittenberg, who also is very extremely careful about everything, told me, the only case they use of Dirichlet in the classical case, when you look at you look for primes which are congruent to B to B mod A, the case when congruent is 1 mod A is simpler. It's known. It's easier proof. And so that's the analog of this which is used. So it's just, anyway, so that's this basic lemma here. Okay. So this is going to replace the argument with Dirichlet in the field extensions which we had before. Okay, so we're going to apply, so we apply this to what? So we look at, so now we look at the product of the alpha V minus EI, alpha, okay, so alpha Vj equals 1 to capital N times Bi to the power minus capital N. Okay, so I look at this. So we had, remember we had this equation here. I hope it's still there. Is it still there? Oh gosh.
GV, no?
This was the, yeah, it's here, okay, it's here. Okay, with alpha V, this is alpha V. And we just take the product for all the various alpha V's. So you get a Bi to the N. Okay, we get a Bi to the capital N. And so it's a norm. So this thing is a norm from Ki over K of something over Kv. Okay? Okay, so we look at these elements, and these are the Xi V's, which we take here. The ones which are there.
There should be another norm.
There should be another norm?
No. This is a norm, but in the first hour, in the first part,
yeah.
we talk, there should, I mean, one norm was equal.
Yeah, there's no which I don't know. I think this one we will not have it. So, but it's, I think it's because we're, there was, in previous case, there was this polynomial P which was irreducible. And so here we have this field extension corresponding to P. Whereas here what we have is we have K cross K cross K cross K. That's the difference. So that's, I think that's where it is. It's here. Okay. So this is, yeah. This is basically the norm. Anyway, so, okay, so we apply to this psi V. And then you produce, by this result, there exists a Ci in K star, such that what? Such that which is so close to these things here for V in S, and then the Ci satisfy this property over there. Respect to S. So at this point I should have fixed a point V0. So I want a V0. So I fix a V0, the V0 which is here, split in all Ki's. Okay, again, Chebotarev, which is not too far from Dirichlet, again, tells me that there exists such V0, not in S, which splits in all the Ki's. And now, okay, so now what happens is that, so what happens is that Ci, so the conclusion that Ci bi to the capital N is close to product of the alpha j is 1 to n of the alpha j minus ei for V in S. This comes from here. Okay, Ci is close to this thing here, so Ci bi to the n is close to that one. Okay, so we have this for V in S, and then the primes V in the decomposition of Ci bi to the n, which are away from S, are split in each Ki, in Ki. So something I should have done is when I choose my S, the S I should take it good. So we produce the Bi. The Bi's were produced, so the S is good for the Bi. So Bi is in OS star also. Okay, the Bi had been produced by this first argument. We throw them into the S, okay? And so you're here. So the Ci is over there. So the V's in the equation of Ci bi away from S are split in Ki. Okay, now we look at G of t, the polynomial constructed by, so we do approximation for the QV of t. So the GV of ei is this. This is GV of ei. Okay, this quantity here.
Maybe you need to construct, you have a familiar polynomial.
Yeah, and so we're producing a global one. Yeah, that's what we're doing now. Okay, yeah. So now you take, so now we approximate the QV of t. So find Q of t, close global, and of course that's not it, close to QV of t, monic, and so on. Integral. So here we just use stronger approximation away from S union V0. So V0 is the one which we allow denominators. Okay, and so we find this G of t. And then for the other one, well, we just take this quantity here, which we're going to throw in here. Except that there's a trick, is that there's a sign here. So G of t equals P of t times Q of t plus sum from I equals 1 to d, yeah, of product t minus ei divided product j different from, sorry, product t minus ej, j different from I, divided by product of the ei minus ej, j different from I, times, then there's a, if you compute, you find that you have to put a minus 1 to the power capital N times Ci bi to the n. So this is the close point we're after. Okay. So I think of this irreducible polynomial. So again, there was some other place which I choose in order to get a close point. Otherwise, so I made it close to some irreducible polynomial so that it is irreducible. Okay.
Do you like to substitute something for t?
So t, what do I get? So I get the g of ei. G of ei is precisely -1 to the n times ci bi to the n. Okay, that's okay. And so the claim is that if I look at this close point, above this close point, I will have points in all the completion.
For each I?
No. This is a sum for all I. So we have a global thing. No, this is the value of g at the value ei is this. And then I'm claiming that if I look at this polynomial in t, and this defines a close point of P1, I look at the fiber above it. The claim is that this fiber has points in all the completion.
No, I didn't get it. So you have this g of t.
Yeah.
How does g of t defines
a close point of P1?
Of P1.
It's an irreducible polynomial in one variable. So it's a close point of P1. So I find q of t, and so g of t irreducible. Okay, that's me.
Depends the point on P1 over.
Well, over some field extension of degree precisely of degree n. I mean exactly n, the n we choose.
It's not an integral point.
Well, we have to discuss. It's nearly integral at lots of places, and then it's the same story. Except that this time we're going to show that it has points in all the completions. We're not going to use a reciprocity argument in the end. It's producing. There will be no reciprocity argument in the end. This one will have the property that in all the completions it has a 0. Okay. So I mean we're nearly finished here. Okay. I think I can erase this one. Okay. Well, I mean, so g of t is in where is it? G of t lives where? In O S. So the ci are integers away from S. The bi are also integers away from. So the ci are integers. They are the ones which are given by the HW lemma. Okay. So they are integral away from S union V0. So gi is 0 of t. And maybe some other place V1 which was not important to make it irreducible, but it's basically this here. Okay, and g of t is very close to gv of t for v in S. For v in S. The gv corresponding to solution. So when we look here, okay, so let's define the field capital L is by definition k of t divided by g of t. Okay, so for places W of L with W above a place V in S, then I claim that the fiber X, so M is this close point.
Which has a more subtle point.
What?
Which
are the more difficult? Well, it's the good places. I mean, well, so anyway, for this place, it's finished. Okay, so XM of LW is not empty because the G of T was very close to the GV of T, and above the GV of T we had solutions. Okay, so because it's close.
This is simple case.
This is simple case. Okay. Now, for the places which are okay. So now, in fact, okay, this is why I want to make this drawing. So here I have my point CIs. And here I have G of T equals 0. So I have EIs here. And so the G of T, well, it does something like this. It gets some EI, E1, E2, and so on, okay? So if I'm away, if I look at the reduction of my family above this variety, at the points which are not on the EIs, I'm in business, because it's Langway-Nisniewicz. Okay, so away from these points, so away from this, away from, and remember, the G is integral, so this is very important, in fact, in the first way. So it's very important that the G is integral away from S and V0. So it doesn't mean the fiber at infinity. Okay? The fact that it's integral means that it doesn't meet the fiber at infinity. So we're really looking just here. Okay? So here, there's nothing that meets here. So away from these points, away from this, the fiber xm of LW is not empty by Langevin-Nisniewicz. Okay, so the problem is at such points. Okay, you're right. It's absolutely the point where we have a problem. Okay, now what is the point? This is a point where G of EI is 0.
Before we wanted to succeed, saying that there is just one such a point. Now, okay, let's continue.
No, I mean, now we're going to look at all the possible points. Okay, so this is what we're taking. The intersection corresponds to OS of t divided by G of t, comma t minus EI. This is exactly this intersection here in terms of rings. So, but this is G of OS. This is OS divided by G of EI. Okay, and G of EI is what? Where's G of EI? G of EI is -1 to the n Ci bi to the n. Okay. The bi was a unit anyway away from some things, so we don't care. But the Ci, which was gotten by the Harpas-Wittenberg lemma, what was it? It was not a unit everywhere. It was integral. But at the places where it was not a unit, we knew that the places that came up were split in Ki. So at the place, so if I'm at a place here, V, where this is where this actually happens, then the G of EI, the G of EI, maybe it has the prime PV, but V splits in Ki. And then we're in business. Because this fiber, you see, we had this fiber, so this point it also lies on this EI. And here what do we have? We have the fiber XEI, which contains this component Y, which is, say, some open set, which is over the field Ki. And then here's K. But because the place splits here, so Y over Ki is geometry integral. So you have a Langevin-Nisniewicz at that level, but because your place V splits, you have points in the completion.
You used this argument already several many times. I mean,
yeah, to get the splitting. Yeah, of course. In the case with rational points, we use the same argument, except that we're using this very strong conjecture, this HW star conjecture for rational points. Whereas here we're using this thing, which this lemma, which is quite easy, in fact, which uses just strong approximation. And so that's the end. Okay, so you're going to be free. It's 3:30. I mean, we have points everywhere. Okay, we have points in all the completions. So of course, I mean, to organize the argument, I should have said this at the beginning. I look at an open set of this variety where it is smooth over this. I put in S this finite many primes.
So, just last question is.
Yeah.
Once again, where you did get rid of the bilinearity condition?
By using Poitou-Tate. Poitou-Tate. We use Poitou-Tate, and we use the formal lemma for torsors instead of using the formal lemma for the Brauer group. So instead of using Brauer of K, direct sum Brauer of KV, Q mod Z, we use H1KT goes to product of the direct sum H1KVT, where there's no ability business here.
And Brauer group uses ability linearity because of class field theory.
Yeah, because you always reduce. It's basically because you use characters, and characters they have to do with with version Q mod Z. Each time you reduce to some. I mean, you always.
Class field theory.
Yeah, it's class field theory, but of course it's all class field theory. I mean, the Poitou-Tate is also class field theory. Poitou-Tate is also class field theory.
Where did we use Poitou-Tate here?
In the formal lemma for torsors. So when I say at the beginning, we can produce some BIs. So I wrote down this torsor, T minus EI equals norm Ki over K of something. This is a global torsor over my X. And I said, if there's no Bramah abstraction, then I can produce some global BIs such that the system has points in order completion. This is the formal lemma for torsors, which uses Poitou-Tate. Because you produce classes in the direct sum of the H1. Yeah, I mean, it's a trick because actually torsors you reduce the Brauer group. So you use the fact that there is no Bramah abstraction to show that there's also no abstraction using torsors under arbitrary tori. But it's a trick of using torsors and arbitrary rather than just say normally you take things like sums of co-restrictions of symbols. And this was not enough. So in the papers with Sansuk and Svendler, we're always using this business, taking sum of co-restrictions with symbols. And so there was always some Abelian extension involved in the symbol. So that gives you a pretty good idea, I think, of their argument. And of course, it's more sophisticated, but this is the simplest, non-trivial case where you can see their argument. And the paper is incredible. I mean, it took me last night. It took me 3 hours to. I mean, I was to produce this thing here. Yeah. No, but I mean, to produce the right thing, not to miss a place. I mean, you must control all places. I mean, okay. So next time, I hope. So I suggest for next time is that I will. So there are 2 possibilities, but I think
the conference there will be. Well, next time is still.
So there's still no, it's not the conference, and then afterwards there's a discussion what will happen. I mean, possibly next time will be the last time. I mean, of course, the Thursday afternoon is free during the conference, but this is a bit people should be free. And then I leave on the Thursday after that. I leave on the 25th. So I mean, if people are excited, I can do something more the week after the conference at the beginning. Say Tuesday or Wednesday. But next week, so what I was planning is to tell you, so there are 2 possibilities. Either I tell you something about integral points, or I tell you something about FQ of C, the Tate conjecture, instead of number fields, discussing this conjecture of a function field in one variable of a finite field. And
what is FQ of C?
A global field of positive characteristic.
FQ of T. FQ of curve.
FQ of a curve. Sorry, FQ of a curve. FQ of a curve, and some connection with unidentified H3, and and Tate conjecture, and how this is how you can. So there are some conjectures about the integral Tate conjecture for curves on a threefold, which actually imply this conjecture about 0 cycles. So I mean, possibly this might be more attractive than integral points for you.